Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are doing the diploma questions of the electromagnetic radiations. As you all know that we completed that unit C, electromagnetic radiations. Now we end that unit with the diploma questions. So this is like the diploma questions which are on the diplomas. So that questions we have from this unit. The in the missions type experiment, an eight-sided mirror is rotating at 17000 rpm. The measured value for the speed of light is 2.7 raised by 8 meter per second. We have to find the distance between the mirrors as well. So we have to find the distance. So we have to find the t in this, and we have a speed which is our v. We have an eight-sided mirror, so this is something we have to define over there. This is called like 170,000. This is the rpm, means the revolutions per minute. So this is per minute, which is from the 1 minute. This 1 minute should be like converted into seconds to get into rps, because the seconds we want. So we convert this is by 1 meter. We have to divide this by 60 seconds. So when you solve this, you get about 2833.333 repeating. We get RPS from here. This RPS is this is called like revolutions per second, and the definition for frequency is the same. That something which is the repeating the cycles in per unit time. So this means this is given us as a frequency. So we say that this is the frequency in hertz now. So we want, so for distance we have like delta d is equal to v times delta t. We have delta v, but we don't have delta t over there. So for delta t we have to do this thing. So for this we have to find the period now, because we do that questions that for eight-sided mirror we do 1/8 times the period to find the delta t. We got one that period from here, so it's 1 upon frequency. So we put the things in. So when you do this, you get the frequency of about 3.5294 into 10 raised to power minus 4 seconds. This also has the units for the seconds. You put this over there, and 3.5294 into 10 raised to power minus 4 seconds. When you solve this, you get your delta t of about 4.4117 into 10 raised to power minus 5 seconds. You put this thing over there with the speed multiplying by the 4.4117, so minus 5 seconds. When you solve this, you get about 11911.7647. But you know that when you have to find the distance by your own, you have to divide this by 2. So at the end, you have to divide this by 2. When you divide this, when you solve this, you get about 5955.8823 something meters. But we want in kilometers because all the options are in kilometers. So convert this in kilometer by multiplying by 100. You get 5.9 kilometers. Divide this by 100. So you get 5.9, which is also the 6.0, because in option you have 6.0. So the D is your right option for that. So that's how you can find these questions. These are like very messy ones, so you have to be like this MCQ. So I do like that. If the written response, you have to be in the sequence. You have to be in a like nice way, not like that way. So that's all you have to do, and that's your answer. Let's move on to the next one. Is more like a theory one question from the mirror. The question says the object is placed far away from a convex mirror. So this is called a convex mirror now. So for a convex mirror, you have to be like everything for the convex mirror we have, which are the following best describes the image. So we have to find out what's that the image best describes this. So this is a convex mirror, and for convex mirror, you will have like 3 things you have to know for that. The firstly, the type is that for the virtual, and this is like the upright image you get always, and you have a diminished one, which is you can say the smaller image. So for the convex mirror, you have to know this. Convex mirror, you have to know this. The focal length is less than 0, but this is not like that mathematical one. So you have to just know the things like we have to find the which describes the best test. So firstly, they mention that the image is upright and smaller, which is the right thing. Then they mention the inverted, but they not be inverted. They should be the smallest. And then again, this not the option, inverted and larger. And the last one is also not the option. So the option is that this one, upright and the smaller, because we know that this is upright and the smaller means the diminished. So the option number A is your answer. A is your answer. So you can see that we have like a very like a type of the theory question in the chapter. Like this is the mirror question, and we not have to directly draw the mirror or the tree diagram. We have to know the concepts of that to do that type of questions. So in mathematical analysis, we also have to do something like a knowledge of this to solve that questions. Like in this one. So if the question says an object is placed 15 centimeter in front of a convex mirror that has a radius of curvature of 22 centimeters. So what is the magnitude of the image magnification? We have to find the magnification in this. So we have something is given to us. So it's 15 centimeter in front of a convex mirror, which is DO. This is a convex mirror, means your focal length should be less than 0, which is negative. You have a radius of curvature, which is R. You have to find the magnification, which is M. So for magnification, if you have like DO, if you also find a DI, so you can use this formula to find the magnification. But our main focus to find now DI. So DI can be found from here. So you have this formula, which is the mirror formula. So you can find the DI from here, which is 1F minus 1 upon DO. But you don't have F. You find the F from this radius of curvature. You know radius of curvature is 2 times the focal length, which means the focal length is equal to the radius of curvature divided by 2. So 22 divided by 2, you will get 11 centimeters, which should be negative because this is a convex mirror. So you put this in now, minus 11 centimeters, minus 15 centimeters, and when you solve this and you do all the thing, the reverse of this two, so the all thing you know from here, and you get the negative 6.346 centimeters. The calculation you know that you have to do the reverse, minus 1, then do the solve. You get this in negative because of a convex mirror, and this will show that for negative sign will that this has the virtual image, which is right for the convex mirror. Now you have to put this in over there. So minus 6.346 centimeters. Divide this by the 15 centimeter. Centimeter cancel out. This minus goes to plus, which you get the 0.42. No units for magnification. So answer for this is now B. So B is your answer, 0.4. And this will show that 0.42 will show that this is the less than 1. So this is the diminished image. So you can see that for one thing you have to do the 3 formulas in the one. So you have to follow this. And this type of question are frequently given in your like MCQs, one numeric one. So that's all you have to do. So let's move on to the next one. The question says a liquid has an index of reflection of 1.38. A time it would take for the light to travel through 15.0 kilometer of this liquid is. So you have to find the time, which is delta t, you can say. So for the time, you want a distance. So you have a distance, which is 15.0 kilometers. So for the time, you do delta d upon v. Delta t is 15.0 kilometer. You want a v. But you have like 1.38, which is the index of reflection. Index of reflection is given to you, which is the n. So n is equal to c upon v. You want v, which is c upon n. So c is 3.00 into 10 raised to power 8 meter per second. N is 1.38, no units. When you solve this, you get this about 217,391,304.3. This is so big answer, and this is your velocity. And you have to put this over there. When you solve this all thing, and one thing more, this should not be in kilometers. This should be in meters because you have a meter per second. So this should be in like meters. So you have to divide this 15.0, multiply this 15.0 with the 1000, and you will get the 15,000 meters. Not in kilometers, it should be in meters. So delta t you will get about 6.90 into 10 raised to power minus 15 seconds, minus 5 seconds. So this is your time, and minus 8, no, minus 5. So D is your answer. D1, D option. So as I told you, I repeatedly when we're doing this topic that you beyond that vector question that you have to solve for n, you have to solve for v. You get the like one of the formula, like you have to find the distance, you have to find the time for the to connect this question with something. So in the diploma questions too, you get these type of questions like in this. Let's move on to the next one. The question says light enters a glass medium n is equal to 1.49 at the angle of 28 degrees with the respect to the surface. The wavelength of the light in the air is 420 nanometers. Determine the wavelength of the light in a glass. So this is type of question of the Snell's law because we have a double things in this. First that thing that light enters a glass medium with respect to the surface. So this means your first one is your 1.0, which is the air one, your n1, and your n2 is 1.49, which is the glass. You have an angle of 28.0 degrees in the light, which is your theta 2 now in the glass. Light in the glass, which is your theta 2 in that case. And also your wavelength of the light in the air is given to you, which is the first medium, which is your L1, lambda 1, which is the wavelength 1. And you find the light in the glass, wavelength in the glass, which is wavelength 2 you have to find. So main focus is to find the wavelength 2. So for this you have n2 upon n1, and you can use that much formula, which will is n2 upon n1 and the wavelength 1 upon wavelength 2. There's no need for any angle. They just give you angle for your confusion. That this value is not used in this type of thing, because we have everything for the wavelength 2. We can't use the angle in this. So n2 times wavelength 2, n1 times wavelength 1. I have to find this n1 wavelength upon n2. So n1 is 1.00, wavelength 1 is 420, nano has the value of 10. So you left this in nanometers because your options are all in nanometers. So you left this in nanometers. You get the answer in nanometers. Divided by n2 is 1.49. When you solve this, you get about 281.8 nanometers, which is also a 282 nanometers. So which is the B option for that. 282 nanometers. That's how you have been solved. This angle is only for your confusion, that might be this used in this question. So you are rigid with that angle. But there's nothing. You have to use the Snell's law, the second equation for Snell's law. That's all the thing you have to do in this. So this is the from the Snell's law. Let's move to the next one. Again, the theory-based question. The question says you have some properties of light, and the transmission of a light through optical fibers depends on the properties. So they mention the word optical fibers, which is a hint for this question. That if the light should be passed from the transmission of the light is passed from the optical fibers, so which property is like very suit with that? So which property is very like contrast with that thing? So optical fibers is the main hint, and this is from your topic. So this is the topic we do when we do the critical angles, when we do total internal reflection, which is TIR. In that I will mention that the optical fibers are the thing which is the application of the total internal reflection that we'll use. So now your whole focus is to find that if the any option is related to the total internal reflection from the 1.5, so that was the right thing for that transmission of light to optical fibers. That is the main property of that. So let's figure it out. So first one says the light can be polarized. So this will confuse you somewhat. The optical fibers can be connected with the polarization somewhat, but not with like every person, like not every person can have this. But the light can be polarized is not like in this option. Because light can be polarized is be the thing when we compare the light as a particle. In this we call about the only reflection thing. Reflection is a type of particle we're doing, but this is not like thing which is connect with polarize, because we're doing with optical fibers. And polarize is a topic which reflects the filters, transmission filters. In that we use a transfer and the longitudinal waves thing. There's more like a wave thing in that. So which means that this first option is not with us, that we don't want this option. The light travels in a straight lines. This is might be the option, because in reflection we do the light be in the straight line, like is a straight line, then they bend, then they like do anything in the other medium, but they should be in like straight line. So this is like option which we consider with that, which is the second one. Next one we have like can produce interference patterns. They don't produce interference patterns. Again, that thing that this involves the wavelengths. This involves the wavelengths, because the thing we do in like a screen and a slits, this all thing the wavelengths we do with the interference patterns in the diffraction one. So then the third option is not valid for that. So this is like thing which we do in the waves, not the particle. We more focus on this for the particle things, because reflection can be done with the particles. Fourth one, when the light is reflected, the angle of incidence is equal to the angle of reflection, which is again a straightforward property that reflection is that has a law of this law of reflection, that index of reflection is equal to index of angle of incidence is equal to angle of reflection. So fourth part is that within an optically dense materials, total internal reflection occurs for index of reflection greater than a certain critical angle. This will again the straightforward one for the total internal reflection. So fifth one is right. So your options is like second, fourth, and fifth, which is the C part. So that's how you have to be consider your things, consider your thinking is a theory that we done in the chapters, because theory based chapter have that type of questions and you have to figure it out how can you solve that questions. So that's all. So let's move to the next one. The question says, for a young double space experiment, the diffraction gradient has 900 slits per millimeters. When a monochrome electromagnetic radiation is shown through a gradient, the distance between the maxima is 11.0 centimeters. The distance from a gradient to a screen is 26.0 centimeters. Find the wavelength of the electromagnetic radiation. So make sure your wavelength should be nanometers or the micrometers, because they mention like this. Okay, so they mentioned this is from the diffraction gradient question, and they given us this thing 900 slits per milliliter, which means millimeter, which means that this is your 1 upon d, and you have to convert this into d. So convert this into d. So 1 upon d is with 900 slits per mm. This means when you flip the d, this will also flip this thing. And you have to solve this now. So when you solve this, you get about 0.01111 mm, which you now convert this into meters, because you have to use in the formula to find the wavelength. So you have to convert this into meters. So which means 1 meters is equal to the 1000 mm, which is the millimeter. So this mm cancel off this mm. So you get about 1.111 into 10 raised to power minus 6 meters. So what's the formula you want to use? So there is a distance between the maxima. Distance between the maxima means you have a distance between the maxima, that the point of bright spots to the distance to all that distance is called the x. So x is given to you in that case. Diffraction gradient to the screen is the L. You know that this is the L. So before doing the wavelength thing, we have to find that if the angle is greater than 10 or not. So for this you have x and L, so you can find the angle from here. So do the reverse of 10, 11.0 divided by 26.0, and when you solve this you get about 22.932 degrees, which is the theta greater than 10 degrees. So you have to use the same thing which we use, that this formula you have to use for wavelength, not that small n approximation. You have all the things. You have that d 1.11 into 10 raised to minus 6 meters divided by the sine of 22.9 degrees divided by n. So n is not given. If it is not given, you take it as 1. So you solve this whole thing and you get about 4.329 into 10 raised to power minus 7 meters. Have to convert this into meters, nanometers. So convert this. This will like multiply by the divided by the 10 raised to power minus 9, and when you divide this you get about 433 nanometers. So you have to divide this for nanometers. So you get 433 nanometers, which is that A option. Not the micrometers, this is the nanometer. So you're going to confuse you about that options they given us. So that's all you have to do. Firstly, solve for 1 upon d, solve for d. Then solve for angle if it is greater than 10 degrees. So use that formula. If not, so use the smaller approximation. This is like a straightforward, which not involve the angle. Make sure when you're solving your calculator be in the degree mode to solve that angle. So that's all you have to do. And this is very important questions, that type of thing. When you given us that thing, slits per mm, lines per mm, that all thing you have to do. Let's move to the next one. And in front, mono 150 volt bulb emits the light with a wavelength of 1.80 micrometers. Total energy of 30.0 photons emitted from the bulb is this. So we have to find the energy. So for the energy type of thing, you have to solve for the, you have n over there. This is your n. So this photons are emitted. And this 150 is given, which is your W, you can say. And your wavelength is also given to you. So to find the total energy, that you have to find the total energy. For total energy, you have a formula n times the energy of the photon. You have to find the energy of photon. You have to find from the wavelength. You have that formula. This is the Planck's equation. Put the things in. Make sure you like put the things like in joules. So put the things like joules. 6.63 into 10 raised to minus 34 joules per second. This is 3.00 into 10 raised to power 8 meter per second. At the end, we convert this into EV. So do whatever you want. So 180, and you have a 10 raised to power minus 6 meters. When you solve this, you get 1.105 into 10 raised to power minus 9 joules. Put this thing over there. So n is given to you 30.0, and this is 1.105. So it's 0.5 minus 9 joules. When you solve this, you get 3.315 into 10 raised to power minus 18 joules. So what is it to EV? So 1 upon 1.6 into 10 raised to power minus 19 joules. Joules cancel out. You get energy total of 20.7 EV approximation. This is the rounded value. So you get 20.7. This is the answer. So again, this thing not used in this. So let's move on to the next one. The question says the monochromatic electromagnetic radiation with a frequency of 1.10 10 raised to 15 Hz is shown on a metal surface with a work function of 2.80 eV. Maximum wavelength, the possible to emit the electrons from metal surface is what? So you have to find the wavelength. And you have a W for this, you have a frequency. You're not mentioned this is the minimum frequency. So this is your actual frequency you have. To find this, to solve this question, so what thing you have to follow, like you have a W, you have to find the wavelength. So you know that you have one formula, W is equal to H times the threshold frequency. And you know that threshold frequency is C upon wavelength max. So from here you can find the wavelength, maximum wavelength. So you don't have the threshold frequency, you have a frequency, but this is not the threshold frequency, or not mentioned this is the minimum. If they mention this is a minimum frequency, that means this is a threshold, but this is not the threshold. So this is equal to the HC upon the wavelength max. Wait. W is equal to this. For wavelength max, you have a HC upon W. So put the things down, and H should be in your EV dot second, because your energy, your energy is in EV, your volt. Divide this by the W, which is 2.80 EV. When you solve this, you get this about 4.44 into 10 raised to a minus 7 meters. Convert this to nanometers by divided by 10 raised to minus 6. You will get about 444 nanometers. C option. So that's all you have to find. Let's move to the next one. Can't add the written response in your like diplomas, but we like follow those questions because sometimes those questions are very important. Like that type of question, you get the diagram and you have a two subparts in that. So let's do the question. The magnifying glass is placed in a stand shown as shown. It is located 10.0 centimeter above the ground level, a ground, and designed to provide 400%, which is 4x magnification of the object. Assume the image must be upright. Image is upright. What type of lens would be here? Where is the object placed for magnification? So this is the lens type of question, and they mention that you get the resume that image is upright. This will give you the answer for this question. You're talking about the lenses, and in lenses you have like a thing that which is called the convergent lens, which will behave like a convex mirror, which is like a virtual image, upright image, and diminished image. So you can use that information for this. So they mention that this is the upright image in the lens. In the lens, you have a convergent lens for that. In the mirror, you have a convex mirror for that. And you have a virtual image, you have upright, you have a diminished image for that. Yeah? And for the B part, you find the focal length for that. So find the focal length. So over there, I find. So for focal length, you've given us that this 10.0 centimeter above the ground, this is the lens, is above the 10 meter centimeter, which is the type of a DO. This is type of DO if you state it as a mirror. So you have given the DO in this. So DO is like 10.0 centimeters. You know the magnification, this given us some kind of magnification. You know the magnification thing. So magnification is equal to 1 minus 1 di upon do. So from the di, you get the minus m and do. Magnification given to you, which is the fourth dimension over there, that this is like 400%, which is the 400% divided by the 100, which you get to 4. So magnification given to you 4. So do is 10.0 centimeters. So all this you get minus 40.0 centimeter because there's a virtual image, that's why you get the minus. You have to find the focal length, which is that plus minus 40.0 centimeters. You do all the thing, reverse of this, solve this, you get 13.3 centimeters. You have to know this. How can you solve the reciprocals? When you reverse this, one other thing also reverse, and this will get your answer. So you solve both parts, and these are the answer for this. Is a short written type of question, like of about 3 to 4 marks, not very much. So that's all you have to do with that imagery. And this is by the and this will do the unit complete that from here. So we completed that unit, and from here your electromagnetic radiation is completed now, that whole unit, and we completed the 3 units from the grade 12 physics. Now we'll have only 1 unit, which is the atomic physics, which is the very easy unit where we conclude all the 3 topics in that all the 3 units in that 4th unit. So this will like be very easy unit. You have a like short unit in that case. You have a short unit and very few lessons you have in that unit. And we will do that unit as soon as possible. And for this, we completed the unit C for this. So that's all for this lesson. These are all the diploma questions which are very repeatedly coming. And you have to practice for all diploma questions. And so learning is EduVibe, learn smarter but not harder. Please like, share, and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till next, get it with EduVibe.